a solar cell demonstration by NASA. So the CubeSat actually, you can see it is here. It's 30 per 10 per 10 centimeters. And it deployed this huge, I think it's 10 meters square, solar cell.
Quick question, how was the picture taken? Was that another?
No, this is actually, no, this is just rendered.
Okay.
Other applications, well, space weather research, upper atmosphere research. There's a nice mission by Swiss universities called Swiss that works actually quite well. Earth observation and many other applications. And actually, I hope that at the end of this presentation, we can talk a little bit about this because, well, it's really nice to have some examples of application stuff that you would be interested in and that nanosatellites could allow you to do. Nanosatellites and CubeSats. So probably already heard about CubeSats. CubeSats are nanosatellites. Not all nanosatellites are CubeSats. So CubeSats are nanosatellites that meet the requirements of the CubeSat design specification, which is a 20 pages long document written by Cal Poly. It basically just defines the interfaces between the nanosatellite and the launcher. So it just basically describes how the spacecraft should look like. So in terms of the dimensions, you have basically three options. 1U, 2U, 3U. So I'm mentioning this because this is something you're going to see if you do research on CubeSats. So this just means that you can put several of these cubes together to form a bigger spacecraft structure. But let's not go into the details.
Tetris.
Sir?
It looks like Tetris.
Yeah. So, but what I'm interested in is this: the fact that Cal Poly standardized interfaces between the spacecraft and the launch vehicle means that we can have a common deployment system. So, the deployment system looks like this. It's basically a jack in the box. So it's a box with a spring inside and a door. You put the cubes inside. And then when the launcher goes into space and wants to release the satellites, it just opens the door and the spring pushes the cubes. So this is how it works. This means that we can basically put this system on pretty much any launcher. We end up with more launch opportunities. And also with cheaper access to space, because we don't have to customize our spacecraft to the interfaces of a particular launcher. So just to give you an idea, these are launchers that launch CubeSats. So there have been about 80 or 90 CubeSats launched so far. Just so you know, these numbers might not be completely accurate. Sometimes it's hard to find information on this, but yeah, this gives you an idea. We can launch CubeSats on basically anything. Okay, so my question is, why don't we do the same thing with internal interfaces of the CubeSat? Because the thing is that most people actually do not want to build a satellite. Most people want to fly a payload into space. They want to launch a payload. I'm asking, what if we could just design a payload according to some specifications, plug it into a standard spacecraft bus, so mission-independent components, and just launch into space. That would make things much easier, because it means that you could just either contract a company to build your spacecraft bus, or buy one off the shelf, or build it yourself, depending on what you want to do. Well, what's the current situation? There are all these companies selling off-the-shelf CubeSat components. You maybe heard about the CubeSat shop. So it all looks very nice. You can buy a complete attitude control system, complete onboard computer. But the point is that they are incompatible. You basically can't buy components from two companies and assemble them, and that's a problem. I mean, it means that you're very limited in choice, and it's not just about compatibility. It's also the fact that you're not buying a complete CubeSat. You still have to do a lot of work. You have to learn how to basically learn how to build a spacecraft. There are some standards well, I don't know if we can really call them standards. This is, for example, the PC104 connector. That is actually a standard. This is used for industrial applications. It got adopted by the CubeSat world, and the problem is that there's no formal specification. Everybody does whatever pleases them. What we propose is to decouple the payload from the spacecraft bus. So it means that, as I said, if you had a system with spacecraft with decoupled payload and a spacecraft bus, you could easily replace the payload by another one, or you could just take your payload and put it on another spacecraft. So, for example, if you negotiated a deal with another university or a company to launch your payload on their spacecraft as an opportunity payload, you could, even if it's not designed for that particular spacecraft. We'd like it to be plug and play, like a PC. You just plug something into your USB port, it works most of the times. Yeah, some people call it plug and pray. Well, anyway. Easy integration of the payload, well, that's pretty much the same thing. Independent development, this is important because you can work on the payload, on your mission actually, without having to learn how to build other subsystems of your spacecraft. You can have two independent teams. You can buy the spacecraft bus from a company. And we'd like to use existing technologies because, of course, we are a non-profit project, or even if we were a for-profit project, we couldn't spend too much time on this. We are trying to reuse as much stuff as possible. And so we are currently developing a prototype for this. So the prototype will basically be a service module. So a small box, I'm going to show you some CAD renderings on the next slide, that will integrate the typical functions of a CubeSat. So an onboard computer, electrical power subsystem, attitude determination, communications. And so basically, if you want to extend the functions of this service module, you just add mission-specific components on top of it. And plug-and-play redundancy. So what I mean by this is that you can take two of these service modules, assemble them, and all your subsystems become redundant. If one fails, the other takes over. So the service module will look like this. Well, this is just this is not very accurate. I mean, this is an early prototype, but it's basically just a small part of a CubeSat. So as I showed you, CubeSats are 1U, 2U, 3U. This would be about 0.2U. And so it means that 0.8U would remain for your payload, for your actual missions. So this is a great improvement compared to traditional CubeSat missions, where the payload occupies usually something like 1/3 of the satellite. These are potential configurations. So here's your payload, here's your spacecraft bus. Same thing here, except that we have some redundancy. We have two modules. And the important point here, everything we're doing is open source. I don't like to focus on this point because there are many projects, space projects, that claim to be open source. So some of you mentioned some of these projects that are on Kickstarter. These are great initiatives. But for example, ArduSat was mentioned. This is a great project, but it's built with off-the-shelf hardware, non-free hardware, that you can't really reproduce. There's only one company making this. You can't get any schematics for that if you are not a paying customer. So to me, it's not an open source spacecraft if everything except the Arduino payload is not open source. Another important point, built from readily available components. So it doesn't make sense if we publish schematics on our website, full documentation, and nobody can actually reproduce it because they can't buy the components. So this is particularly an issue with ITAR. So the other, I heard, I was at a presentation at the SpaceUp conference in Stockholm, and somebody from an American university was presenting an open source project. And when we asked them, okay, so can we get, well, we're interested, we'd like to get the source code. No, it's actually only for American entities because it's ITAR protected. So, I mean, really, what's the point? So, no, in our case, Americans, Europeans, or Russians, they should be able to build the spacecraft. This is another point I wanted to show you. So, no, this is not a satellite, this is a smartphone. But you realize that in a smartphone, many of the subsystems actually match the subsystems of a small satellite. So here, well, I'm not going to explain the acronyms, but you have the onboard computer, you have the radio, altitude determination. Okay. So couldn't we just take a phone and launch it into space? Well, some people are working on projects like this. So this is PhoneSat, made by NASA. So you can see the smartphone here. So they basically just took a smartphone, put in a cube, a special structure, and it's going to implement some of the traditional functions of a satellite. Surrey satellites in the UK are working on something similar. However, it's not really viable because you have lots of dead mass. You don't need a screen in space, or unless you're an astronaut, of course. Unsuitable radio bands, so mobile phones do not work in space. You cannot communicate with them. Interfaces, how are you going to interface with your payload? And difficult to customize. You can't really do, can't really change the layout of the server, for example. So this is just a quick note. What we did actually for our reference implementations, we got inspired by mobile phone technology, and we used components that were originally designed for mobile applications. For example, the ARM7 CPU that we use on our onboard computer. I'm not going to go into technical details, but the fact is that you can, one important point with small satellites is that you do not have to buy radiation hardened components. We are talking about low Earth orbit. In low Earth orbit, has been proven that commercial components that you can buy anywhere, as long as you design your spacecraft properly with respect to the radiation environment, it will work. And actually, most CubeSats do not use any radiation hardened components. So it means that you can really, all the components that are needed to build CubeSat, you can easily buy them. You can build your own satellite. So software. One important point in space, you have very limited resources. On a CubeSat, you have about 1 watt of power. So your mission has to take that into account. So we do some fancy resources management. You can check out our website if you want to see some details of that. And again, our software is based on existing technologies, so the Linux operating system. But of course, the important point here is that you can use existing technologies, but you have to manage risks and see the limitations. So, for example, in the case of our computer, we know that we're going to need some hard real-time tasks. So this means that, for example, if we have some, for example, the control system needs to perform some maneuvers, well, it has to be performed at an exact time. So we have a secondary CPU that does only this, but this limits, this maybe increases slightly the complexity of the hardware, but it makes the development process much easier. So just to conclude, well, building a spacecraft is not easy, I can tell you that. But if we start standardizing components, defining clear interfaces, we can make that process simpler and eventually even make it simple enough so that anyone, any hobbyist can build their own satellite. We have to use existing technologies. This is one of the big problems of the space industry. We cannot reinvent the wheel. We have to see what's done elsewhere in other industries. I think that applies universally. And OpenCube is open source. You can download all the documentation online on our website. You can join the project. You can collaborate with us if you want to work on cool space hardware. Maybe even fly your own payload at some point. That would be, you're more than welcome. And we think that we all have to work together. I think this is my conclusion. In space projects, we can't look at the nationality of people like the Americans do with ITAR. We just have to all work together. Yeah. This is our website, our Twitter feed. So thank you. So what? I don't know how much time we have left.
Yes, maybe like a couple of minutes.
So yeah. So I'd really like to know your like your opinion on nano satellites. What applications would you like to see? If you have any cool ideas about that. Yeah.
The agency guys is the so I think it's great, what you just said. I mean, those applications are important, and you have to move nanosats out of this toy image that they have, like you said. And there are two things I'd like to say. One is very important that agencies cannot do very well is technology demonstration. You said that that's very important. The other thing, the standard argument I hear in the corridors when they talk about nanosatellites is the typical criticism, and I'm not that on that side, but they say, let me play the devil's advocate, space debris is an issue. So every time you speak about nanosatellites in front of somebody from an agency, show them also that why it's not a problem, show the lifetime of the nanosatellites and make them aware that you're very much thinking about this. And I know you're thinking about this, and that's important to
very important point. Actually, the official CubeSat specification says, the newest version says that the lifetime of CubeSat should well, the CubeSat should re-enter within 25 years' time.
Yes.
So
Okay.
that's so it means that you cannot call your nanosatellite a CubeSat if it doesn't.
Yes.
It's
Exactly how it's supposed to be. And if you show that every time that you're fulfilling what's required, perfect. Nobody can criticize you for that. And don't try to go to 5 years.
Well, actually, that was a bit leading to the question that I had, because indeed there is a lot of criticism on CubeSats because it is generating space debris sometimes from day one, because there is a lot of failure rate recently, or up till now. There was a huge failure rate on CubeSats. Some of it didn't even start or work for, what, a few hours? Isn't there, or do you think there is a potential trend that we make these CubeSats a bit more reliable, or a bit more, how should I say, they will probably be more expensive, that they can last for several years, maybe 1.5, 2 years? Because then, again, you will put space debris up there. It will be the same amount of space debris, but the return that you get from the satellite will be a lot bigger for that same small cube that you have.
Well, there are actually missions there are CubeSats up there that still work perfectly fine after several years in orbit.
But it's just
and
a few ones.
yes, and this is a very interesting point, because what we should do is to learn from these CubeSats. Okay, so what makes them actually last that long? And it comes out to the fact that we do not learn from our from the experiences of others. Everyone builds everything from scratch. With this concept, we can improve on our previous attempts. So if we see that some decision was actually not very good, well, in the next iteration, you just change it, and until you arrive to something that's reliable enough. Of course, you cannot never have 100% reliability.
No,
That's important.
it's a matter of balancing, because if you go for...
But I completely agree with you that if we have to improve the reliability of CubeSats, if currently the reliability is actually, well, it's around 60–65%. It looks actually worse in most papers, because they count launch vehicle failures as spacecraft failures. So of course, if they tell you that only 25% of CubeSats work well, it's just because we are using all the Russian ICBMs to launch them. Yes?
Maybe just to add something to this, if you consider microsatellites launched by students, it's almost the same failure rate. You just have to consider that all the CubeSats that are launched right now have been built by students. So it's a student shop, and it's not a perfectly good work.
May I add on that? Actually, I don't think that's really a space debris problem, because space debris problem is collisions in sun-synchronous orbit. And they're adding thousands of fragments by one collision. And then if you have a CubeSat that fails, you have one object that lives 25 years max. Even if it explodes, the fragments will live less than 25 years, so it's gone in a very short period of time. So the trouble is not in that region. The trouble is at 700 to 1200 kilometers in sun-synchronous orbit. That's where the trouble is. And we have to keep, like a mantra, we have to repeat that message. Nanosatellites are not a problem. Nanosatellites are not a problem. So if we do that enough, like Charles de Gaulle, after each UN speech, he said, "Vive la France." We have to do that.